So here it is, the final honors physics homework assignment. Homework number 29. There would have been homework 30, but we've just run out of time. Homework 29, conservation of momentum. So I'm going to be solving some problems where I apply the law of conservation of momentum, realizing that the total initial momentum of a system is equal to the final momentum. So let's get into it and see what happens. Here I have, in the first question, a giant egg that explodes as part of a fireworks display. The egg is at rest before the explosion. When I read that, it says to me that there is no initial momentum. It's not moving. It has mass, but no velocity. So therefore, no momentum. And then when it explodes, it breaks into two pieces. One piece goes in the positive x direction, and the other piece is going to go in the opposite direction. Because if the total momentum is zero before the explosion, the total momentum has to be zero after the explosion. Now, there are two parts, A and B. Their momenta change. It's the total momentum that doesn't change. So let's read the questions here. What is the magnitude of the momentum of piece A before the collision? Well, before the collision, there's no momentum whatsoever. So the momentum of A before the explosion is equal to zero. In part B, during the explosion, is the magnitude of the force of piece A on piece B greater than, less than, or equal to the magnitude of force B on A? This is Newton's third law. Newton's third law, in some way, is the basis of the law of conservation of momentum. It states that for every action, there's an equal and opposite reaction. These two pieces, A and B, exert equal and opposite forces on each other at every instant in time. The component of the momentum of piece B, which is the piece that's going to move in the positive x-axis direction, is measured to be plus 500 kilogram meters per second squared. There's no way that I know how they got that number. It's the mass times the velocity, however those work out. They put a plus sign in front of it because object B is moving in the positive x-axis direction. I would presume it has positive momentum. Momentum is a vector. If you're moving in the positive direction, you have positive momentum. If you're moving in the negative direction, you have negative momentum. Since the total momentum is conserved, if B has plus 500 to the right, then A must have negative 500 to the left. So the answer here is simply negative 500 kilogram meters per second. And that's the end of problem one. On to problem two, where I think in problem two, we're actually going to get to apply the law of conservation of momentum in its equation form for the first time. A man is standing on very slick ice and he fires a rifle horizontally. The mass of the man, together with the rifle, is 70 kilograms, and the mass of the bullet is 10 grams. Be careful there. It's 10 grams. You have to convert to kilograms. 0.01 kilograms. The bullet leaves the muzzle at a speed of 500 meters per second. What is the final speed of the man? Well, I'm going to apply the law of conservation of momentum to this. So what I'm going to do is write the conservation of momentum out in its basic form. MAVA plus MBVB is equal to MAVA prime plus MBVB prime. Now, it's a man standing on ice with a rifle and a bullet in the rifle. Everything has a velocity of zero. Before the trigger is pulled, everything has a velocity of zero, which means the momentum of the man and the rifle and the momentum of the bullet are both zero. It's totally okay that the initial total momentum of this situation is zero. It's just like the egg explosion from the previous part. And as such, if I want to solve this equation out, I'm going to subtract MBVB prime to the other side of the equation, flip it as it were. What it says is that the momentum of the man after shooting the rifle is the opposite of the momentum of the bullet after the rifle shot. So since I know that the bullet has a mass of 0.01 kilograms and a velocity of 500 meters per second, I can calculate its momentum. That momentum is equal to the momentum of the man. So here in my equation, I would have negative 0.01 times 500, and then I would just simply divide by the mass of the man and the rifle together, 70 kilograms, and that would give me the velocity of the man afterwards. That velocity would work out to be negative. The problem is asking me for the speed, however, so I can put it in without the negative sign, just the speed of the man traveling in the opposite direction. Problem number 3, I have a 20,000 kilogram railroad car. It's rolling along at 4 meters per second. And I'm going to dump an 8,000 kilogram load of gravel into it. What is the speed after the gravel is loaded? This problem is a classic. Here's what the algebra looks like. Again, I start with the law of conservation of momentum in its basic form. But I realize that first of all, the first thing I realize is that before the gravel is dropped into the cart, its velocity is 0. The railroad car has initial momentum, 20,000 kilograms times 4 meters per second. But the load has no momentum at all. So this term is going to be equal to 0. You see that in my next step. MAVA is all alone on the left-hand side. On the right-hand side of the equation, the mass of the railway car and the mass of the load are going to move together as one object. When the load is dropped into the railway car, they move along with the same final velocity. So what I've done is I've factored that same velocity. VA prime and VB prime are equal to the same velocity that I've just called V. I probably meant to put a prime on that, but it's not going to affect my solution at all. So I have the initial momentum of the railway car is equal to the total mass. I'm just treating the railway car with the load in it as if it has, the mass has increased, a total mass, MA plus MB. Dividing MA plus MB to the other side gives me the final speed of the railway car. Not surprisingly, the railway car will slow down because its mass has increased. If the momentum is to be conserved, the velocity has to decrease. Very, very classic problem of conservation of momentum. Problem number 4. Well, this one's crazy. The parking brake on a 1,000 kilogram Cadillac has failed and it's rolling slowly 5 miles per hour toward a group of small children. Seeing the situation, you realize you have just enough time to drive your 2,000 kilogram Volkswagen, which is quite surprisingly twice as massive as the Cadillac, into head-on collision with the Cadillac to save the children. What speed should you impact the Cadillac to bring it to a halt? Well, the Cadillac has some momentum. In order to stop the Cadillac, you're going to have to bring into that situation the opposite momentum, equal and opposite, so that the total momentum is equal to 0, so that when you collide, you both come to rest, stopping the Cadillac and saving the children. Well, I don't have to do any unit conversion here. The mass of the Cadillac is 1,000 kilograms and the speed is 5 miles per hour. But all I have to recognize here is that my Volkswagen is twice as massive. If it's twice as massive, I only have to go half as fast. If I have twice the mass and I go with half the speed, I'll have the same momentum as the Cadillac in the opposite direction, which means the total momentum will be equal to 0, which means after the collision, we'll all come to rest and the children will be saved. Problem number 5. 3 identical train cars coupled together are rolling east at 2.2 meters per second. They have momentum. A fourth car traveling east at 4.5 meters per second catches up with them and they stick to make a 4-car train. A moment later, they hit a 5th car that was sitting at rest on the tracks. It couples to make a 5-car train. And so what is the speed of the 5-car train? Well, what I have is I have objects colliding and sticking together. So, strangely enough, I don't have the right equations for this one. Shooting crackers. All right. Well, I'm just going to bring in the law of conservation of momentum. So I'm going to start with 3 identical train cars. They have a mass of 3m and a velocity of 2 meters per second. So for MA, I'm going to put 3m and 2.2 meters per second. I have another car traveling in. It has a mass of m and is moving at 4.5 meters per second. So here I'm going to put m times 4.5 meters per second. That is equal to, they collide and stick together. So it's going to be 3 plus a 4th is going to be 4m multiplied by their mutual velocity. So let me say that equation again. I have 3 times 2.2 plus 1 times 4.5 is equal to 4 times the final velocity. I just said the numbers there and not the masses because you have a mass in every term and the mass cancels out. So you can solve that equation for them after the collision. And then you have to solve the problem again. So you have these four cars going along with a particular velocity, and they're going to collide and stick together with yet another car. The mass is still unknown, but it's going to be on both sides of the equation, so it'll cancel. And so this equation the equation that I derived for two cars coming and sticking together, that will solve the problem for the next phase, and I'll have calculated the final speed. $300-gram bird, that's a 0.3 kilogram bird flying along at 6.4 meters per second, sees a 10-gram insect, that's 0.01 kilogram insect, flying straight toward it with a speed of 26 meters per second as measured by an observer on the ground, not by the bird. The bird opens its mouth wide and enjoys a nice lunch. What is the speed immediately after swallowing? Well, you have the mass of the bird and the velocity of the bird. You have the mass of the insect and the velocity of the insect, but the momentum of the insect is negative. When they collide and they stick together, the right-hand side is going to look like this: the mass of the bird plus the mass of the bug times the final velocity. And you can solve for the final velocity of the bug. You just have to be careful that the momentum of the bug is negative. Tennis player swings a racket. Tennis ball's coming toward her. It's just like the one with the bug. The tennis ball has negative momentum, and that's where most people go wrong with this problem. The tennis ball has negative momentum. So when I do my law of conservation of momentum for this problem, I'm going to have the mass of the racket times the velocity of the racket minus the mass of the tennis ball times the velocity of the tennis ball is equal to the mass of the racket times the velocity of the racket after impact. That is the quantity that I'm looking for, plus the mass of the tennis ball times the velocity of the tennis ball after impact, which will be positive, and I'm given. So I can solve for VA prime, easy peasy, lemon squeezy. In part B, if they're in contact for 11 milliseconds, what is the force that the racket exerts on the ball? There are two ways you can go here. You can either calculate the change in momentum of the ball and divide by the time, or calculate the change in momentum of the racket and divide by the time. Either way, you'll get the same magnitude of the value for the force. Be careful. The time is given as 11 milliseconds, pardon me. That's 11 times 10 to the minus third seconds. So a little care with the units there is necessary. That would be the end of that problem. Moving on to problem 8. 300-gram cart, that's 0.3 kilograms, moving at 1.5 meters per second on a track when it collides with a larger cart at rest. After the collision, the small cart recoils now recoils, that means goes backwards. That means this is a negative velocity. What is the speed of the large cart after collision? It's just conservation of momentum. The small cart, the initial momentum of the large cart is 0. The small cart, where this velocity of the small cart after the collision is negative, and then the large cart, solving for the final velocity of the large cart. A bullet, again in grams, 0.08 kilograms, fired into a wood block at rest on the table. The block with the bullet embedded slides 5 centimeters across the table. Coefficient of friction, oh my God, what's going on? Well, it's law of conservation of momentum, to be sure, and it's the bullet sticking into the block. So I write the conservation of momentum and realize that the block, which is MBVB here, has 0 momentum, so that's 0. And then after collision, they stick together. This is a problem I've solved before. I got this equation. So VA is the initial velocity of the bullet, and that's what I'd like to know, but I don't know the mutual velocity of the bullet and the block stuck together after collision. So I need another equation to bring in. I have an unknown VA and an unknown V prime. I need another equation. Well, the equation is going to be the law of conservation of energy. After the bullet embeds itself in the block, The bullet and the block together with a total mass m have kinetic energy. Negative work is done by friction over the displacement delta x to remove that energy so that the final energy is equal to 0 when the block skids to rest. Solve this equation for v prime. Plug v prime into this equation and solve for VA. Woo, fun. Even more fun. Coming to the end now. Number 10. Bullet again fired into a block, but it goes through the block. No, it doesn't go through the block. Oh no, it sticks. It embeds itself in the block. It sticks in the block, and then it goes flying off the end of the table. It's projectile motion brought back from early in the course. It's a collision where the two objects stick together. Here it is. But in this case, I know the mass of the bullet and I know the velocity of the bullet, so I can find the final velocity after the bullet embeds itself in the block and it flies off the table with an initial horizontal velocity. You work out this projectile motion and you'll find that the distance that it lands from the bottom of the table is equal to the horizontal speed that it travels, multiplied by the time it has to travel that distance. Well, since it's falling from the edge of the table, that is h high, that's 60 centimeters, that's 0.6 meters, everything MKS please. The time it has to fall is the square root of 2h over g. Multiplied by the velocity is going to be the distance it lands from the end of the table. How exciting. Conservation of momentum in a projectile motion problem. That is super special. Ooh, the last problem. The geologists, they believe that the dinosaurs were, when we were struck by a large comet, throwing up so much dust that the sun was blocked out for a long period. They give me the mass of the comet, and they give me the impact speed of the thing. So I know its momentum, and we want to know what the recoil speed is after the collision takes place. Well, I'm going to do this situation here, where I'm going to take the mass of the comet times the velocity of the comet divided by the total mass of the comet and the Earth together. And you'll get that recoil speed. Because the mass of the Earth is so extraordinarily large, that is going to be a very, very, very small velocity. To demonstrate that, they want you to compare that velocity to the velocity of the Earth around the sun. Well, in order to calculate that, which is a calculation you've already done earlier in the course, you simply take the circumference of the Earth's orbit, 2 pi r, where the radius of the Earth's orbit is 1.5 times 10 to the 11th meters, and divide by the time it takes the Earth to orbit the sun in seconds, which is a year's worth of seconds. Take the recoil velocity calculated from part A, and divide by that orbital velocity and express it as a percent, a very, very small percentage. So when this asteroid collides with the Earth and kills the dinosaurs, it doesn't really do much to affect the orbit of orbit of the Earth itself. How about that? Homework 29, conservation of momentum, COVID-19, Shidley out.